Okay, thank you very much. Good morning. It's my pleasure to present to you in a very, very quick way major findings and conclusions of Chapter 24 entitled Policies for Energy Technology Innovation Systems. So before I do that, I would like to start first with a definition. And being at Stanford, I do not apologize at all for the academic prose of this definition. In our chapter, we have defined energy technology innovation as the embodied result of institutionalized research, development, and deployment efforts driven by collective learning processes involving both suppliers and users of technologies operating in specific contexts of adoption environments and incentive structures. Again, I don't apologize for the academic prose here in Stanford University. Presenting a chapter that is extremely rich is challenging in 17 minutes, so I give you a kind of selective preview and a personal assessment of an assessment. So what's new? I think what is new, you find particularly at the bottom of this slide, quite uncharacteristic for international assessments. This chapter has an assessment, it has a literature review, but it also stimulated a lot of new independent research, which is also contained in the chapter. And it also stimulated specific case studies where we have looked into success and failures of technology innovation policies. These 20 case studies are a companion to the GEA volume and will be published separately. So this is not only the traditional review, it also embodies new research, and this research is actually ongoing and continuing. So this is a living document and a living chapter. What's new in the chapter? I think there are new concepts. We have developed a new concept which we refer to the Energy Technology Innovation Systems Perspective, or ETIS, in order to frame the chapter. There is also a concept which we refer to as granularity, which refers to the small unit scale of technologies, which is an important explanatory factor for the relative success or unsuccess of different technologies. The chapter is also quite empirical. It has new quantifications on global resource mobilization. You have seen some numbers already yesterday, and you will see them again today. We have assessments on R&D efforts in emerging economies, which is new, compiled by a team at Harvard University. We have looked into quantifications of knowledge depreciation, on the impacts of policy misalignments and volatility, and on the quantification of a systemic innovation portfolio bias. I'll show you some results in a second. Given that this is a global assessment, we did not assess particular policy instruments. Instead, we looked and developed at guidelines, generic policy guidelines that focus on managing knowledge flows, in particular knowledge feedbacks and spillovers at the international scale, on policy stability and alignment, and finally on some recommendations on what are the targets for an energy technology policy, which basically should be a systemic approach to innovation and portfolio-based. In the interest of time, I'm going to skip the next slide and show you a simple illustration of what this Energy Technology Innovation Systems perspective is all about. At the core is the development of technology as it proceeds through successive stages of a technology life cycle, involving specific processes of innovation that are characterized by continuous knowledge feedbacks. So this is the center part of this graphic. As you move from the left to the right, you need to move across the different stages, involve different innovation processes, and invoke continuous knowledge feedbacks. Surrounding this kind of technology-centered lifecycle perspective are the four major dimensions of innovation systems, which is knowledge, the generation and learning of knowledge, which are actors in the institutions. We have heard about this already quite a bit. At the bottom are the necessary resources that need to be mobilized, and finally on the right-hand side you have the technology outcomes in terms of improvements in technology characteristics like performance and costs. This sounds very abstract. I give you here a simple example. This is from a case study done by one of our authors, Greg Nemeth. He's an American author, and it shows you what we call a virtuous development cycle in an energy technology. It's a historical case of concentrated solar power here in the United States. And the point of this graphic is not to confuse you with a complex flow diagram. It's just to highlight that we need to open the black box, again, reference to Stanford University, of technology beyond simplistic notions of cost buy down or learning curves or things like that. We need to look really deeper into inside what happens in technology. And the basic message is we always need to consider innovation as being both supply push and demand pull driven. So we need both factors, okay? We need innovation being stimulated by new knowledge, which in this case improves the efficiency of a technology. We need demand pull stimulus that invokes economies of scale effects that can be positive but also negative. It depends on the technology. And finally, we need also stimulus through continued experimentation and learning that improves the operational reliability and therefore the output of this technology. All of these different factors work together to lower the costs of this technology. A virtuous development cycle between 82 and 92, and that's the key message, that virtuous development cycle came to a standstill. It stopped because of public policy discontinuity. So it's also a nice illustration about the importance of policy stability and continuity in assessment. You have seen this graphic already early in the presentation of Wim Turkenberg, and it gives you some kind of cost trends plotted against the traditional measure of learning curves. Now what you see here is actually quite a heterogeneous picture, and I will try to explain you why this picture is heterogeneous. But I would like also to draw to your attention that with the exception of solar PV here, all the technologies, all the alternatives to fossil fuels have seen significant cost escalation after the year 2000. So cost escalation is not specific to nuclear. It's also characteristic for wind turbines in the US, for offshore wind projects in Europe, and it's also characteristic for the very successful ethanol program in Brazil. So why do we have these cost increases? Well, there is evidence, mounting evidence of negative economies of scale, and there's also increasing mounting evidence of significant policy feedbacks. And we need to entangle these policy feedbacks beyond just simply saying, okay, let's subsidize this technology more. If the subsidy actually leads to a policy response in terms of strategic pricing strategies of firms, read increased profit rates, that might not be the ultimate desirable outcome of a technology innovation policy. Now, let me turn to try to explain you why these different technologies show different learning rates. This is not the final slide, I apologize for it, so it's a very convoluted table. But the basic idea here is very simple. Instead of looking at the traditional metric of learning curves in the energy field as cumulative capacity, we look here simply at the cumulative number of units. How many experiments do you do? How many plants do you build? And this is a review of the learning curves. Green are energy end-use technologies, and red are energy supply technologies. The bottom line is in the averages. Energy end-use technologies have mean learning rates of 20%, and energy supply technologies only of a mean 10%. So why do we learn less with energy supply than with energy end-use? And the reason is also there. With energy end-use, on average, we build 1 billion units in this sample. And for energy supply technologies, we build on average 10,000 units. So for energy supply, 10,000 experiments. For energy end use, 1 billion experiments. And this explains differences in the learning rates. As we learn, we can also unlearn. And this is a novelty in the chapter. It's a chapter on knowledge obsolescence. I have co-authored again with Gregory Nemeth, so it's a very prominent name. So the Stanford faculty might want to consider to hire at some point. And here it tries to explain you why we have these very different rates of knowledge obsolescence. Basically, we have two dimensions. One is the rate of technological innovation, the rate by which novelty comes along, and so therefore, with increasing novelty, we depreciate the knowledge of the old technology. And the second one is the traditional dimension of knowledge depreciation through volatility and turnover of human capital, staff turnover being a classical example. So in cases where you combine high volatility in human capital with high knowledge depreciation due to rapid pace of innovation, cell phones have been mentioned as an example, you have high rates of knowledge depreciation. The interesting finding is that according to our limited assessment of the available literature, knowledge depreciation rates in the energy innovation field are typically between 10 to 30% per year. With these high rates of knowledge depreciation, policy stability moves to the center front. We have done some hypothetical model simulations on the impact of the knowledge stock of different policy regimes, and we can show that actually the way how money is spent, how public resources are mobilized, is as, if not more important, than the absolute amount of money of actually mobilized. So, don't think only about how much money needs to be mobilized, you need to think about the time pass of this money mobilization, and it might be more wiser to start small and increase gradually but stable than to do a big splash and then run out of money after 2 or 3 years, because with these high rates of knowledge depreciation, you will lose within a few years all of the investment in the new knowledge generated. A second important finding is that we need to invoke much more the international knowledge flows and spillovers. This gives you some finding from the empirics. This is a first quantification of public and private R&D, energy R&D expenditures in the emerging economies. And as you see on the left panel, on the bar chart, actually in absolute numbers, the emerging economies, Brazil, Russia, India, China, and South Africa, actually start to approach the level of energy R&D in the OECD countries. So this is quite significant. The downside of this is, as you see in the color code, is that the R&D portfolio is even more biased in the emerging economies compared to the OECD. There's hardly any energy R&D into efficiency, and there is an undue overemphasis on fossil energy, which is in kind of contrast to the needed transformation which we've heard about yesterday. Also significant is that these rapidly emerging new knowledge powerhouses in the technology innovation space are systematically excluded from international technology cooperation. This gives you the kind of participation in the international technology collaboration programs organized through the International Energy Agency, and you see how limited the number of non-OECD or non-IEA countries are in this kind of international technology cooperation. Let me move to the next example, and this refers to alignment, consistency of policy signals. This gives you a quantification of the global resource mobilization in energy technology innovation across all development stages of a technology, and into 3 broad categories: energy end use, energy conversion, think about power plants, and finally resource extraction, coal mines, oil fields, etc. So this is only the fraction of the global resource mobilization that is directly influenced by public policy. So either through public expenditures, typically in R&D, or through forced policy instruments, like feed-in tariffs or portfolio standards, as listed in the niche market segment. What you see here is basically that we spend actually very little on energy end use. We mobilize little resources through public policy and end use. We mobilize a lot of private sector investment into renewables through policies, but this push of renewables into the system is actually counter-caricatured by the big block of $500 billion of subsidies that are diverted into maintaining fossil fuels in the system. So how consistent as a policy framework is that? You mobilize resources to push a new technology into a system, which at the same time you subsidize to keep the incumbent in. 5 times as much as you actually mobilize money to introduce the new technologies. This is a key issue. So policy, stability, and alignment, hopefully relatively contradiction-free, and this is one of the core policy design criteria which we have come up in our assessment. Let me conclude with a short illustration of a SQL research which we have been doing, also using this energy technology innovation framework. And basically here we have extended the framework to a more systematic assessment. We have examined more than 40 different indicators, where we differentiate between inputs into the innovation system, the black circles, from the outputs of the innovation system, So inputs are R&D, technology roadmaps, analytical models and modeling studies, technology collaborative agreements, market formation, incentives like feed-in tariffs, etc. And outcomes of innovation are learning effects, social rates of return on innovation, and future needs of technologies as distilled from the scenario literature, including the GEA scenarios. Now, 40 indicators looking at the match between inputs and outputs of the innovation system. And this gives you the assessment. All of the inputs into the innovation system are systematically tilted towards energy supply technologies. And all of the desirable outputs of the innovation system are all dominated by energy end use and efficiency technologies. So, the framework helps you to understand why we conclude that there is a systemic innovation technology portfolio bias, which needs to be addressed if you want to manage the transition towards the kind of technology pathways which the GEA scenarios have described. I would like to use this opportunity to thank my authors. They are listed here, and to direct your attention to the additional resources which are available. It is the GEA chapter itself. There are the 20 case studies which are also posted already online. They will be also published as a separate book volume by Cambridge University Press. And similarly to Kirk Smith's chapter on health, we have also produced a more accessible condensed summary which is produced, which has been published in Annual Review of Environment and Resources. I thank you for your time. Thank you.